So due to the fact that we had 4 lectures canceled last week, I am making a video that covers the concepts for Chapter 3, which you're going to be responsible for. I will, however, do all calculations in lab, and we'll have a worksheet as well. So we're going to start our discussion with a comparison of microchemistry in a way versus macrochemistry. So we'll be looking at atoms and molecules and how we represent the masses of those and grams. So the first definition you're responsible for is atomic mass. And this is the mass that you see, well, I take that back. We'll get to the mass you see on the periodic table. But by definition, the atomic mass is the mass of an atom of an element in atomic mass units, or AMUs. Remember, all numbers require a unit associated with them, or they don't mean anything as far as measurements go. So atomic mass, or the AMU, atomic mass unit, is relative to the carbon-12 atom. So by definition, one atom of C12 weighs, or has a mass of, 12 atomic mass units. So that means that one AMU is equivalent to 1/12 the mass of a carbon atom. Okay. And here, also shown on this particular scale of AMUs, we have hydrogen with 1 proton, 1.008 AMUs, and oxygen with 8 protons, 16 AMUs. So the atomic mass is relative to the carbon C12 element that has exactly 12 atomic mass units. However, the working, or what I'm going to call the working definition of atomic mass, is an average. So what the mass we see on the periodic table is the average atomic mass for naturally occurring isotopes of an element expressed in AMUs. So for example, lithium exists has 2 isotopes, Li6, Li7. This percentage to the left, it represents how much of each isotope is found in nature. So clearly Li7, is far more abundant than L6. So to represent the atomic mass of lithium, we take an average. I do this a little differently, but this is the way your text does it. So when I work problems with you in class, I will show you the way I do it. Essentially, it's just converting these to decimals before I do the calculation. So the average atomic mass for lithium is going to be, in this method, the percentage times the mass of that isotope plus the percentage of the second isotope times the mass of that, and divided by 100. So the average atomic mass of lithium is 6.941. Now, if we were just presented with this data and asked to predict whether which element, or which isotope, is more abundant, because of the large degree of separation between those percentages, we could predict that the average atomic mass would be very close to 7. And in fact, we do see that, having that average atomic mass at 6.941 AMUs. So once again, looking at that periodic table, it does show the average atomic masses. And here you see lithium, 6.941. So we see the average atomic mass and the atomic number. Remember that atomic number tells us how many protons are present. Okay. Today, atomic masses of elements, and we do have new ones being synthetically made in laboratories, are measured using what's called a mass spectrometer. Okay, so this is a diagram of what that looks like, and down here we have a graph of what the data output looks like too. And this analysis is of the three isotopes of neon. We have neon 20, 21, and 22. And as you can see, based on those peaks, their relative abundance is significantly different. Neon 20 is the greater in abundance. 21 much smaller, only 0.26%, and neon 22 is about 8.8% of naturally occurring isotopes of neon. So let me explain the mass spectrometer, and this is the technology that again is used today to measure or determine masses. And in this example, what's going on is a gaseous sample is injected into the spectrometer, and it is bombarded by a stream of high energy electrons. And what this does, it transforms those gas molecules into ionized fragments that have positive charges. And those positive charges are accelerated through a mass analyzer. So here are the acceleration plates, down to a detecting screen at the other end of this apparatus. And the masses then are determined based on the degree of deflection. So these are the different points at which those charged particles are hitting the detection screen, and that screen enables then the determination of the relative mass and abundance of those particular isotopes. Oh, and here we go. Sorry about that. The lighter particles are hitting, the deflection is here, heavier are here. So deflection is greater for those lighter particles. And once again, that neon 20, 90.9% abundant, so the highest abundance here. So we commonly have terms for amounts of items. For example, when we buy a carton of eggs, we usually, although you can buy 18, the most common grouping or packaging for eggs is a dozen. And a dozen to us means 12. When we think about pairs of shoes or socks, they always come in twos because hopefully, well, never mind, but 2 means a pair, so a pair means 2. So the chemist also has what it calls its term for a number of things, and that's the mole. It's abbreviated by MOL, and this is the amount of a substance that contains as many pieces as there are atoms in exactly 12 grams of carbon-12. Okay? So the mole can be applied to anything though we'll use it only for atoms and molecules, but we could talk about a mole of basketballs, or a mole of pennies, or a mole of marbles. It represents a number, and you're all familiar with that number, Avogadro's number. We will use 6.022, so we will limit that number to 3 decimal places, and it is times 10 to the 23rd. This is a very big number, okay? But as you can see, it does have more significant figures as we're going to be using. So when this is used as a conversion factor, it will be considered to be an exact number. So what is molar mass? Okay. Molar mass is the mass of 1 mole of whatever we're talking about. Again, that could be eggs, or shoes, or marbles, or atoms, or molecules. And that molar mass is in grams. So atomic mass is in atomic mass units. Molar mass is in grams, all right? So 1 mole of carbon-12 atoms equals Avogadro's number of atoms, and that equals a mass of 12.00 grams. 1 carbon-12 atom has an atomic mass of 12 AMUs. So essentially, the average atomic mass that we see on the periodic table is used, or the numerical value is used as the mass in grams for 1 mole of whatever that element is. So 1 mole of lithium atoms is 6.941 grams of lithium. So for any element, the atomic mass in AMUs is equal to the molar mass in grams. Next terminology, or next definition, molecular mass or molecular weight. And this is the sum of the atomic masses in AMUs in a molecule. So here we're looking at SO2. We have 1 sulfur atom, and we look on the periodic table. It has a mass of 32.07 AMUs. We have 2 oxygen atoms. So we add to that sulfur mass 2 times the mass of oxygen to get the molecular mass of SO2 in atomic mass units, which is 64.07 AMUs. Similarly, for any molecule, the molecular mass in AMU is equal to the molar mass in grams. So that means that 1 molecule of SO2 has an atomic mass of 64.07 AMU, and 1 mole of SO2 has a molar mass of 64.07 grams of SO2. Now, remember when we discussed ionic compounds and covalent compounds, we said ionic compounds, the formula is called a formula unit. Molecular compounds, the formula is called a molecular formula. So formula mass is the representation of the atomic masses in AMU in a formula unit of an ionic compound. Calculated the same way molar mass is calculated, except it's for the formula unit, and we call it formula mass. So given sodium chloride, One formula unit is NaCl. One sodium atom, one chloride atom. Add those together and we get the formula mass for sodium chloride. So for any ionic compound, formula mass in AMU equals the molar mass in grams. So 1 mole of sodium chloride has a molar mass of 58.44 grams of sodium chloride. We're going to jump topics. Now, I will do calculations in class with you for this material, but as I said, I'm covering the conceptual slides and we'll do calculations in class. So now we're going to look at chemical equations. So we're going to talk about the way we represent a chemical reaction. And of course, the chemical reaction is a process in which one or more substances is changed or converted to one or more new substances. The equation is the recipe. So we use in the equation, we use the chemical symbols to show what's happening during that process. And there are 3 ways here shown representing the reaction of H2 gas with O2 gas to form water. These are, again, those space-filling models of H2 molecules and an O2 molecule. And we get 2 molecules of water. We could also represent that as kind of a sentence. 2 hydrogen molecules plus 1 oxygen molecule gives us 2 water molecules. Or more commonly, we use the symbols and coefficients to indicate how many there are. So 2 H2 molecules reacts with 1 oxygen molecule to give us 2 water molecules. Reactants are always on the left side of the arrow and products always on the right side of that arrow. So how do we read these chemical equations? Once again, 2 atoms of magnesium plus 1 molecule of O2 makes 2 formula units of magnesium oxide. This is an ionic compound. You have a metal and a nonmetal. We could also read that as 2 moles of magnesium plus 1 mole of O2 makes 2 moles of magnesium oxide. Additionally, based on the law of conservation of mass, we can use or represent the masses that are required to make the magnesium oxide. And if we sum the masses on each side of the arrow, and in this case, the mass of magnesium and O2, that would come to 80.6 grams of magnesium oxide. The way this is not read is 2 grams of magnesium plus 1 gram makes 2 grams. No, 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 no. So the coefficients are representing either atoms, molecules, or moles. So now we're going to focus on balancing these chemical equations, and I am going to walk through the slides of an example. However, we will do a lot of practice in class together. this next week. But the first thing we need to be able to do is write the correct formulas for reactants and products. Okay. So that means you have to have mastered naming and going from name to formula and formula to name. And of course, as we said before, reactants are always on the left, products on the right. So you should be able to write and then balance an equation based on a sentence or two that describes what that reaction is. For example, ethane reacts with oxygen to form carbon dioxide and water. So you're not responsible for organic compounds, so I don't expect you to know the molecular formula for ethane, for example. Excuse me, I would give that to you, but you do need to know that oxygen is one of those elements that exists as a diatomic molecule. So gaseous oxygen is O2. And of course, you need to be able to give me the formula for carbon dioxide and obviously water. So this tells me that C2H6 plus O2 gives CO2 and water. However, this is not balanced. So that's what we need to focus on next. We need to use coefficients in front of these formulas to make the number of atoms on each side of the equation for each element the same. We do not change subscripts. For example, the 2 and the 6. That is not proper. This is a totally different molecule from this. Okay. So, coefficients go in front. We don't change the subscripts. A good approach is to start by balancing elements that appear in only one reactant and one product. Make life a little bit easier. So for example, we've got carbon and hydrogen in only one product, or each in only one product on the product side, but oxygen appears in both. So we're going to save oxygen for last. And we'll be using this O2 to balance our oxygens. So I believe this slide's, well, let's see where we start. Starts with carbon. So we have 2 carbons on the left, and we only have 1 carbon on the right. So we need a coefficient in front of CO2 to make 2 carbons. Okay. So now we have C2H6 plus O2 gives us 2 CO2, and water is not yet balanced because now we're going to look at hydrogens. We have 6 on the left and we have 2 on the right. So what can we multiply, or what coefficient can we use in front of water, the water formula that is, to come up with 6 hydrogens? 3. So we're going to put a coefficient of 3 in front of that water molecule. So now we have 2 carbons, 2 carbons, 6 hydrogens, 6 hydrogens. Now we can take a look at oxygen. So now we're going to balance the oxygen atom, which appears in both products. Okay. We have 2 oxygen on the left. We get 4 oxygen from carbon dioxide, 3 from water. So we have 7 on the right. And we have to put something in front of this formula that multiplies by 2 to give us 7. Okay. So we're going to multiply O2 by 7/2 or 3.5. Okay. However, coefficients can't be fractions. So that means we have to multiply the coefficients on both sides of the equation by 2. And when we do that, we get 2 ethane plus 7 O2 gives us 4 CO2 plus 6 waters. So we want to go back and double check that all of the elements are still balanced, just to make sure. So we'll go back through and we find we've got 4 carbons on the left, 4 carbons on the right. We have 12 hydrogens and 12 hydrogens. And then of course we just balanced our oxygen, excuse me. I have 14 oxygens on the reactant side and I have 14 on the product side, 8 coming from CO2 and 6 coming from water. So our equation is balanced. Okay, so now we're going to take a look at one of my favorite topics, stoichiometry. So stoichiometry is a big word, but all it refers to is, or means, is that we use balanced equations and to permit us, or the coefficients from the balanced equations that allow us to convert from reactants to other reactants, products to products, in grams or moles. Okay, so here's a diagram that outlines what the basic steps in stoichiometry are. Here we're starting with a mass of a particular compound A, and we can use the molar mass of that compound to convert to moles of that compound. And then using the stoichiometry from the balanced equation, okay, so those are the coefficients or the mole ratios, we can convert from moles of A to moles of B. And then using the molar mass for compound B, we can convert from moles of B to grams of B. So the basic process is grams of A to moles of A to moles of B to grams of B. Okay? But first we need a balanced equation. And if we are given a mass in grams to start with, then we have to convert those masses, or that mass, to moles. Again, that third step is using the coefficients to convert from one compound to another. And then if we're asked to go to grams, we convert those moles to grams, our desired unit. And this is basically stoichiometry. We will do a number of example problems for this. So I'm going to jump on to describing 2 other terms. And whoops, I think I missed maybe a slide. We'll see, just a moment. We need to define limiting reagents. Okay. And here we have the balanced equation for a reaction of NO plus O2 giving us NO2. And there are 2 moles of each of those. And I'm sorry that arrow went slightly askew. So here's a pictorial representation. Here are oxygen molecules. Here's our NO. And you see that, and these are our products, after the reaction is finished, we have these NO2 molecules, okay? And we still have some O2 molecules left. We don't have any NO molecules. So all of the NO has been converted to NO2, and we have extra O2. So NO is the limiting reagent, and O2 is in excess. So that limiting reagent or limiting reactant gets completely used up in the chemical reaction. And it is the reagent on which the theoretical yield of that reaction is based. So, definition of theoretical yield is the amount of product that would result if all the limiting reactant were consumed. Okay. The actual yield is the amount of product that is really made. How much do we really get when our reaction is complete? And then percent yield is the actual yield, how much we really produced, divided by theoretical yield, how much we theoretically could make if all that limiting reactant was used up times 100. And I think that might be the end of our this short video. So again, on Monday, we're going to wrap up naming from chapter 2, and then I will start doing calculations from this chapter 3 material. And